So here in this video, I want to talk about a couple useful trig identities, so trigonometric functions, and how we're gonna apply these functions and identities in our substitutions. So let's start with the most basic one: sine squared x plus cosine squared x equals 1. This is our most fundamental identity, this Pythagorean identity. So this is one that I memorize here. Now, from this one, I can get the other two. First thing I'm going to do, I'm going to divide everything by sine squared x to get the other one. That's going to produce, well, what's sine squared divided by sine squared? That happens to be 1. What's cosine divided by sine? Well, that's going to be cotangent squared x. And 1 over sine squared is cosecant squared x. Okay? Now I'm going to take the same equation here. This is the one we have to memorize, and I'm going to divide through by, instead of sine squared, I'm going to divide by cosine squared. And when I divide through by cosine, sine divided by cosine gets me tangent squared x, and then cosine divided by cosine gets me the 1. And then 1 over cosine squared, that's going to get me the secant squared x. So from this identity right here, we find the other two. And so all three of those are critical for our success. We need to know all three of these identities. And like I said, I memorized this one, and then I memorized how to get the other two if I have for some reason forgotten these other two here. All right. Another one that you're gonna need to memorize is sine 2x. This is the double angle identity, very important here. Sine 2x is equal to 2 times the sine of x, okay, difference between 2x and x, right? Double angle identity, times the cosine of x. Okay, so sine of 2x is 2 sine x cosine x. All right? Something you've just got to memorize. Okay, got to memorize that. Another one you need to memorize is the cosine of 2x is equal to cosine squared x minus sine squared x. This is one version of it. Another version of this identity, if I replace sine squared with what? Well, if I subtract cosine squared from both sides, then I get sine squared x equals 1 minus cosine squared x, right? That's from my Pythagorean identity. If I substitute that in, I get cosine squared. Let me convert this. We'll do red. Why not? Cosine squared x minus, and then in parentheses, this part, 1 minus cosine squared x. And so this will simplify to 2 cosine squared x minus 1. Okay? Another version that you can do, instead of replacing sine squared with the 1 minus cosine squared, we can replace the cosine squared part. If I solve for the cosine squared, I get cosine squared x equals 1 minus sine squared x, right? So going off of this, after I replace that with 1 minus sine squared x, and then minus sine squared x, what do I get? I get 1 minus 2 sine squared x. Okay? Now, why is this important to us? This brings up what's known as the reduction identity. this might be the new one that you may not remember from pre-cal, or it might have been glossed over so quickly, you're not extremely expected to remember it. Pythagorean identities and the double identities, those should be things that you picked up from pre-calculus. So the reduction identity is to take care of even powers of sine and cosine. Now, what do we think of when we think of reduction? We think we're making it smaller, okay? Reduction. So how does this work? So I'm going from a second degree down to a linear, so to speak, sine or cosine trigonometric function, okay? So in that sense of power and that alone, since sines and cosines aren't linear functions. All right, so reduction identity. If I take this fact here that cosine 2x equals 2 cosine squared minus 1, so cosine 2x equals 2 cosine squared x minus 1, then if I solve this thing for cosine squared, I need to add 1 and then divide everything by 2. So what does this get me? This gets me cosine squared x equals what? It equals 1 plus cosine 2x over 2. So this is the first reduction identity. For an even power for cosine squared, we can reduce it from a squared down to a linear with this identity. Now the other one is I take 2 cosine theta, and that's equal to this 1 minus sine squared. So, I'm sorry, cosine 2 theta, right, or 2x, equals 1 minus 2 sine squared x. And so then, if I solve for sine squared, I'm going to subtract 1, and then divide through by negative 2. And when I divide through that by that negative 2, the signs change. I get sine squared x. I'll leave you to do that algebra there to solve for sine squared. And this is going to be 1 minus cosine 2x over 2. So very similar to the cosine squared reduction identity. The only difference is one is a plus and one is a minus. Now, this is goofy, and a lot of stuff I do is goofy, but the way I remember which one it is, the plus or the minus, is if it's cosine, I add the cosine in, and if I do sine squared, I'm subtracting the cosine out. Okay, so no mathematical reasoning to that, just my clever way of memorizing it, if you could even call it clever. All right, so these are the big identities. So let me copy and paste these all in one spot. So if you're a note card person, you want to put them all in one spot. Cool. And you either need to memorize them or know how to find them at any point. Okay, so very important that you know what you're doing here. When it comes to identities, those are all cosine 2x. And then lastly right here. So these identities, they're just going to keep popping up in this integral section. So it's very important that you have a firm grasp of these key identities. Now, other identities you obviously need to know. you need to know that sine x over cosine x is tangent x, right? And then the reciprocal cosine x over sine x is equal to cotangent x, right? These are those easy identities. 1 over sine x is secant x, obviously. 1 over cosine x is secant. Okay, this one's cosecant, this one's secant. Okay, sorry if I said that wrong. Okay. So make sure you know your reciprocal identities. And look, this works both ways. The reciprocal of cosecant x is sine x. So all is good in the world. You do the reciprocals, you get back to where you're supposed to get back to. Okay? All right.